Right. Good morning, everyone. Thank you for coming. Today, I'm going to be presenting my thesis titled A Large Database Study on the Evolution and Performance of Sailing Yachts. This thesis I did over in Southampton, and my advisor was Dr. Joseph Banks. So I'll start off with the outline, then I'll go over the objectives of the thesis, and I'll introduce what is the Offshore Racing Congress, how they gather and process their data, and what were the limitations of their database. Then I'll go over the literature review, then the methods that I used throughout the study, how I derived the equations, and how a factor analysis works. Then I'll show the results of the factor analysis, design trends from the period analyzed, and some performance indicators. Afterwards, I'll conclude the presentation, but I'll also add a slide on how I found a method to exploit the ORC rules. So the objectives were, firstly, to compile a large and unbiased data set. Large, so the results are applicable to as many vessels as possible, and unbiased, so the results aren't skewed either for a racing vessel or a cruising vessel. With that data set, I made equations to derive the relationship between principal dimensions, and especially how those principal dimensions changed over time. I also used those relationships to estimate the performance of the vessel. Finally, I analyzed the ORC rating system as a whole and developed equations to estimate the rating of the vessel. So the Offshore Racing Congress, they are an internationally recognized body that organizes regattas all over the world. In those regattas, they have many types of vessels: classic yachts, racing yachts, cruising, everything. This presents a very difficult challenge on how can an older yacht fairly race against a modern yacht. That's where the ORC rating system comes in. The way the rating system works is pretty simple. After a regatta is done, the lapse times are adjusted by a coefficient, the rating. The rating of a vessel is dependent on the performance of the vessel. If a vessel has a higher performance, the rating will be higher, so the adjusted time will be higher to compensate for that. Conversely, if a vessel has a lower performance, the rating will be lower, and the adjusted time will be lower than the finalized. Why I'm talking about this? The ORC, they were kind enough to make their data available. That database included 8,500 yachts from 40 different countries, and each yacht had 181 parameters. But how was this whole data processed and gathered by the ORC? They firstly start off by 3D scanning the hull. This is a very precise scan with more than 1 centimeter per 1 point per centimeter square, and 180 stations along the hull. From this 3D scan, they put this into a velocity power program software, which is a software used to resolve the forces in a yacht, given the sail arrangement and wind conditions. The ORC, they use the wind condition shown above, so from 6 to 20 knots in 2 knots interval, and those angles shown as above. From this velocity power program, we have the predicted speeds, and then the ORC finalizes by calculating the rating. There are two most used types of rating: either the rating that is used for courses windward, leeward, or when the yacht's racing upwind and downwind, or for whenever the yacht is racing any other type of course. But like anything, this database has its limitations. The main thing was that the average length of the yachts included were just 11 meters, and the maximum was of 44.5 meters. The issue was that the standard deviation was just 2.6 meters, meaning that 95% of all the yachts were between 5.9 meters and 16 meters. Another issue is that the fact that mostly of the vessels included are regatta-ish vessels. The solution for the first problem was very simple: to add larger yachts. This data set had an average length overall of 44.4 meters, a maximum length of 70, and a standard deviation of 9.4. This was done by manually adding an extra 156 yachts to the database. The issue with this is that I had no PP nor performance data from those yachts. So during the literature review, many sources, they include typical values, coefficients, ratios for many types of vessels, but they don't often disclose how they got this data or where did it even come from. Another issue that I found is that there was only one study that analyzed historical trends, and even though it was just briefly mentioned in the report. Also, it was a very small study with only 75 vessels from the 1950s to the 1980s. Most studies fell into either one of two categories: analyzing a already existing population of vessels or parametric iteration design. So I'll go further in depth into these categories. Most studies that analyze a population of vessels included roughly 300 vessels, except for one study, which included 2,200 vessels. The issue is that very few studies use this approach because of how labor-intensive it is to collect all this data. Parametric design, it is a tool that is often used in the late stage of design in order to optimize the whole. The issue with this is that the results are only applicable for vessels with very similar hulls, and of course, you can't analyze design trends. Now, with the background done, I'll go over the methods and specifically how I derive the equations. First off, you pick the parameters that you want. What are the inputs, and the output that you want? Ideally, the inputs should be correlated to the output. I use the factor analysis to determine which inputs had the best likelihood of being a good input. With these parameters, you make a mathematical model. It can be as crazy or as simple as you want. Linear, nonlinear, exponential. The only thing that you gotta add are coefficients because they play a major role on the next step. During the error reduction, it is an algorithm that iterates between several values of coefficients and determines which has the best combination that produces the least amount of error between the model and the final and the actual data. And that's it. You have an equation that can estimate the inputs and outputs. The issue is that this equation might not be accurate enough. So in that case, you can just go and iterate. You can either adjust the mathematical model or just pick different parameters. Now, with this tool done, I'll go over the next one, the factor analysis. Factor analysis is also known as variable important analysis. It is a tool that is often used in psychology because direct correlations between factors aren't exactly clear. It is a method that finds underlying driving factors, such that each factor has a high correlation to variables, but the factors themselves aren't directly correlated. So I'll go over an example. Say you have a set of variables. The variables have some correlation between each other. A factor analysis will be done and determine that there are two underlying factors for this set of variables. And then we'll find that the correlation between each factor, and again, the factors themselves aren't directly correlated. And then that is it. For a yacht comparison, we could say that we have the sail and hull parameters, deck and cabin layout. From this, we can say that factor 1 is a representation of the yacht performance, and factor 2 is a representation of the comfort of the yacht. So I'll go over the results of the factor analysis. The first thing to point out is that factor 1 has a really high correlation to almost every metric. So we can say that factor 1 is correlated to the performance of the yacht. And looking at factor 2, we can say factor 2 only has a high correlation to the beat angle, which is how the ORC refers to the optimal angle to sail when sailing upwind. So we can say that factor 2 is just the beat angle factor. From this, we can say that the beat angle doesn't have a significant impact on the overall performance of the yacht, meaning that how close you can point to the wind when you're sailing upwind doesn't affect your overall performance that much. Another thing that you should note is that the overall variance of the total of the hull and sail parameters are only those parameters are above 1, which is conventionally used as a threshold for this analysis. So I'll go further into those parameters. First thing to note is that 83% of the variance can be explained by the length overall and the length of the waterline. That symmetric sails have no effect on the performance factor, and that out of the 4 sail types, only asymmetric sails have a significant impact on the performance. Now I'll go over the design trends observed on the ORC database. So here we have the blue dots, which represent the data. The red line is a simple moving average with the period of 50. The dashed blue line is the trend line, and the shaded blue area is the confidence interval of 95%. We can see that around 1970s, 1960, the ratio began to steeply decline as it approaches 1 in recent years. This suggests that yachts were built more like this, where they had a large overhang at the bow and the stern and very pointy ends. And yachts nowadays are built more like this, with a vertical stern and bow. Now going over for the length overall and beam ratio, we can see that the ratio declined until the 1980s, then it began to pick back up, suggesting that the vessels from the classic years, they were long and narrow, but the design evolved to become more beamier, especially midships. And nowadays designs have a larger beam at closer to the stern of the vessel. Here we have the upwind performance of the vessel. In the y-axis, we have the beat-through number, which is the velocity predicted by the VPP software that the vessel can achieve when sailing upwind, measuring the through number. We can see that has been very little change in over 100 years of history, to the point to where the performance of nowadays it is still within the confidence interval of data measured 100 years ago. I'll go over those outliers in a second. Here we have the slenderness ratio and its effect. In the x-axis, in the y-axis, we have the jar flow number, which, similar to the beat flow number, it is the performance, it is the velocity of the vessel predicted by the VPP when sailing downwind. We can see that at slenderness ratio of above 6, the jar flow number begins to rapidly increase, suggesting that having a slenderness ratio of above 6 makes significantly easier for the vessel to plane, which increases the performance of the vessel downwind. Some other performance indicators that I found, some other performance equations that I derived are shown above. I will just go briefly over those. So you're gonna see a lot of slenderness ratio because it has really high correlations to the performance. It is a very simple ratio, and it is defined as the length in the waterline divided by the cubic root of the displacement. You also see two equations that describe the ratio between the beat and jibe flow number, which again, it is just a measure of the speed when sailing, the maximum speed when sailing upwind and the maximum speed when sailing downwind. And again, the beat angle, which is the optimum angle to sail in upwind conditions. So going over the outliers. The first one is pretty obvious why it would be an outlier. This is Flying Nika. This is the first fully foiling ORC certified vessel. It has predicted speeds of above 25 knots in just 12 knots of wind. So it's quite clear why this would be an outlier. The second one, it is the Far East 28R. Firstly, it is very unassuming why this vessel would have such a high performance, but digging down deeper, we can see that the sail area to displacement ratio of this vessel is about 20, which is 3.5 standard deviations away from the average of the ORC data. So to conclude everything that has been said so far, the major changes in design were the decrease in the ratio between length overall and length in the waterline, and length overall and the beam. For both data sets, ORC and large yacht, we saw a decrease of roughly 20%. Another ratio that decreased by almost 20% was the length in the waterline divided by the displacement of the ORC vessels, which decreased by 20%. This is likely associated with the fact that this factor also has a high correlation to the slenderness factor, which again improves the downwind performance. This ratio, however, it increased on the large yacht database by 10%, likely due to the implementation of lightweight materials, which decreased the displacement of the yacht for a given length. Another really interesting point to note is the fact that the average slenderness ratio of the ORC dataset is now above 6. Again, which again, going back, is the threshold for non-linear improvements on the downwind performance. I'll go over the equation that I derived to estimate the ORC rating. In this equation, SA down is the maximum downwind sailing area. Delta is the displacement in kilos. The cool thing about this equation is that it has an average standard deviation error of just 2.1% and an average error of 0.9%, showing how precise this equation is. Now I'll go over how to exploit the ORC rules. From the VPP data, when they are calculating the rating, they don't just take an average of the wind speeds. They do a weighted average, and the weighted for each wind speeds are shown above. By picking another distribution of the performance of the yacht, we can maximize the difference between the yacht performance and its rating, making it essentially a winner vessel. So thank you, everyone. Now I invite back Margo and Kira for the Q&A.